Hello, so I'd like to thank the organization for inviting me for this talk. I didn't know exactly what you wanted from me, so I have a general talk on AI that I've given many times, but I think that's way too general for the specialists that are in here. So I tried to set up something slightly more interesting, also slightly more technical. And so the question I'll try to discuss with you here today is, will deep convolutional neural networks be sufficient to take us towards artificial general intelligence? Okay? Before that, let me just give you 1 or 2 or 3 slides on what AI is, where AI can be applied, and what can we expect from the next near future developments in AI. So of course, artificial intelligence is a keyword that is very popular now. Means many things. In some respects, it means things that it shouldn't mean. I myself classify AI in 3 big classes of applications. AI itself, of course, is a set. AI, of course, is a set of techniques that have been developed in the last 6 decades. They include advanced search techniques, okay, to solve problems in state spaces that are very large. They include techniques to represent knowledge, and of course this gave rise to many useful technologies, including databases, but not only. But most of all, AI, and that is the technology that is pushing AI forward, is machine learning. Okay? Machine learning is an old idea. Alan Turing talked about machine learning in his paper in 1950. He even said in that paper that if we want to get computers to become intelligent, it will probably be too hard to program them. The best way is to let them learn, so to program some system that can learn and then let the system learn from experience. And in the last 20 years, in the last 10 years, machine learning has indeed been appearing as the technology that can push AI forward. Okay? The applications of AI are many. So there is a big area of applications where you may call data science, big data, data analysis, analytics, okay? And this basically includes analyzing large volumes of data and extracting economic value from them, okay? So you can use this in sales and marketing. And of course, many of the largest companies in the world, like Facebook, like Google, but also Amazon and Apple, have the value they have because they are able to use your data in marketing, mostly in marketing, but also in sales and other applications like this. But large volumes of data can also be used in process optimization, and Industry 4.0 is actually not much more than using large volumes of data to optimize processes, logistics, distribution, and production processes. It can be used in many scientific applications, in drug analysis, new treatment discovery, discovering new molecules, where you scan huge databases, scientific databases, and you try to find information. It can be used in the analysis and also in the manipulation of social behaviors, like in elections, and of course in the financial sector to analyze financial tendencies, time series, and so on. So this is a new area of application. So data science did not exist, or at least did not exist with this level before we had these techniques in place. Then there is a second area of application of AI, which is this idea that if you have systems that are smart enough, they can be used to replace people, right? People that answer the phone in call centers, people that sell insurance by phone, people that drive cars and trucks, people that are your assistants and schedule appointments and so on, but also lawyers who scan legal documents and look for stuff in legal documents and write contracts and find problems in contracts, and doctors, medical doctors, in particular if they are in the area of diagnosis, right? Radiologists, but also doctors that look at particular medical exams and decide what to do next. All these areas, people will be replaced progressively, not at once, but progressively by computers, by programs running AI, programs based on machine learning. And finally, so the top is now. This will be the near future, let's say the next decade or so. And then, of course, we have the long term. And the long term for AI researchers has always been one single objective, which is reach artificial general intelligence. What is artificial general intelligence? Is the idea that you can have machines that are as smart, as flexible, as powerful as humans, and can learn anything that a human can learn. Okay? Let me say that we are very far from achieving this goal. We don't even know how to get there. We don't even know if we will get there. But people that work in AI and people that have worked in AI for the last half a century, this is what they aim to reach. And it was believed maybe this could not be so hard. People in the 60s, people in the 70s believed that you could get to artificial general intelligence maybe in a few years, maybe in a decade. It has always been postponed. It's always sometime in the future. We have made some significant advances in the last decade, but we are still not there. We still do not know how to get there. So of all these technologies, the most interesting one for several reasons, but also because it's the area where I worked, it's the area where I did my PhD, but it's also, I believe, the area that is pushing AI forward now is machine learning. What is machine learning? Machine learning is a very powerful technique that uses computers in a different way, right? Normally, we think of computers like this, right? Some software engineer, some programmer writes a program. You run the input through the program, you get the output, right? This is indeed as a computer works, right? The problem is that sometimes writing the program is very difficult. For instance, imagine driving a car. If you want to drive a car, the input is fairly easy. A camera can be a camera facing forward to the road, right? The output is also not difficult, right? Basically, to drive a car, you need to output two real numbers. One that is the angle of the steering wheel, and another number that is whether you are accelerating or braking, right? Positive, let's say, if you are accelerating, negative if you are braking. So when you are driving a car, you are actually converting the input, basically an image, in two real numbers. Not a very difficult task, right? But many of you here are software engineers. If I ask you, so this is not very difficult, please write me a program that takes as input an image, from the windshield, and generates the output and drive a car. And most of you will quit right on the spot if I ask you to write a program like this in 6 months, 1 year, or even in 10 years, right? It's very, very difficult to write such a program. Are you with me? You understand why it is so difficult to write such a program? Because this program has to process this input and understand what's in there, right? Is it a road? Is it a child? Is it a traffic light? Is it a train or a truck or whatever? So the actual processing that this program has to do to drive a car only from the input is very, very difficult. So machine learning turns computers on their heads, right? Machine learning does it another way around. Now, what we will do, we'll have here a computer running a machine learning algorithm, and we show it many samples of input-output pairs, and you get the program for free, right? For instance, if you are trying to drive a car, you basically sit the computer next to a driver, right? And the computer looks at what the input is, looks at what the driver is doing with the steering wheel and with the brake and the pedals, and the computer learns how to drive the car. The computer generates the program, right? So you understand that machine learning uses computers in a very deeply different way, right? You don't need to write a program. The program is written only once. If you have a program here that is good enough, you only have to write the program once, because then the program can learn anything. If this sounds too good to be true, is because it is too good to be true, right? And the reason it's too good to be true is that we still don't have here algorithms that are powerful enough, that are flexible enough to learn anything. But they can do a lot of stuff, okay? How do you actually go about doing this miracle? I'll call it miracle for a while. Well, there are many ways to do it. Machine learning has many subfields. There is supervised learning, which is basically what I just described to you. You have a teacher that tells you what to learn. There is unsupervised learning, where you don't have a teacher, so you have to learn by yourself. It's slightly different from what I told you, but still some of the ideas are the same. And there is something called reinforcement learning, where you have a teacher But the teacher is not with you all the time. The teacher is only with you at the end, right? So if you are driving a car, you sit on the car, you drive for 5 minutes, and if you crash, the teacher tells you, you did not do well. You crashed the car. And if you do not crash and you get to where you wanted to go, the teacher tells you, good job, okay? This is actually the way kids learn when we are young, right? I mean, our parents are not with us all the time telling, now you do that. So, you know, if you get burned on the oven, you get some feedback, but it's delayed feedback. So between these three, supervised, unsupervised, and reinforcement learning, there is a large set of techniques that have indeed enabled us to make significant advances in a number of fields. How exactly do you go about, you know, that box that I had there, the machine learning box? Well, there are many ways actually to do that. Pedro Domingos in his book broke them into 5 big families. The analogizers that look for analogies in the data, that look for data points that are near data points that I've already seen, okay? Algorithms that use genetic algorithms, methods that use genetic algorithms, methods that use statistics, basically try to estimate probability distributions, methods that are based on the manipulation of symbols and in finding relations between symbols, and this is why I left it to the end, connectionists, which are today the most powerful, the most flexible methods. Okay? What are connectionist methods? Are basically methods based on neural networks. You have heard about them. But what is a neural network? Neural network is basically a system consisting of many single units. Each of these units implements a very simple function that is vaguely inspired in the function of one human neuron, which basically fires if you have enough stimulation coming in. If you have enough stimulation coming in, then you fire on the output. And what is interesting about neural networks is that, if you encode the weights in the proper way, then the neural network maps the input to the output. That is, it learns to map any input to any desired output, and therefore learns the program. So the neural network is the program that the machine learning algorithm learns, okay? You may not see it as a program because it's a diagram, but this is actually a program, and it's usually a program. I mean, you run, you compute the inputs, you compute the outputs, and you compute all of that. And the neural networks can be trained to perform complex tasks. The neural networks, if you use the right architecture and the right features, the neural networks can learn, for instance, to distinguish faces, to distinguish persons in the audience. And they do that because the first layers recognize simple features, then the next layers recognize some more complex features, maybe eyes and noses and so on, prototypes of faces and so on. And we know that this is also similar to what happens in the human brain. We know that the first layers of the cortex actually do this sort of recognition. Now, why have we been able to make significant advances in the last 10 years in neural network learning in what is called deep learning? Well, basically because of 3 factors, okay? The first factor is that we have better algorithms, better architectures, better methods to train the networks. The second reason is that we have much more data to train the networks, and therefore we can train networks in hundreds of thousands, maybe in millions of images, and train the networks to recognize this. And the third reason is that we have computers that are fast enough to do all this. We did not have these computers, we did not have GPUs, we did not have machines that could be trained with millions of images, with millions or even hundreds of millions of net weights, okay? So if you do this, and this is just a small sample of the set of neural network architectures that have been proposed, right? This is from Google Inception, VGGNet, VNet, one that we used, LeNet from Yann LeCun. So there are many architectures. They are published, you can use them, but even better, you can get them pre-trained. So you can download a pre-trained neural network that has already been trained by millions of CPU hours, and that is already pre-trained so that the first layers do all the pre-processing that you need to perform complex tasks like recognizing faces or recognizing cats, which is one of the favorite train. So I'll just give you one quick example before I go on. This is a network that we used. We used it to learn to identify the results of AVC, of stroke in the future. So this is what we predicted will be the affected regions in the brain, and this is the ground truth, that is the actual regions that were affected in the brain in the future. You can see that the prediction is not perfect, but it's close enough, and in fact this method was amongst won first place in an international competition to predict exactly this development, okay? So this is basically the setup, right? Those are deep neural networks. They are actually called deep convolutional neural networks. Why convolutional? Because each of these layers actually implements a convolution, it is space invariant. So if I shift one pixel to the right, the weights are the same. So convolutional neural networks are invariant to a translation. In this case, the images are 3D images, so they are not pixels, they are voxels, because we are working with resonance imaging, and so the convolutions are in 3D, but you get the idea. If it's images, it's just like the same neural network will recognize a cat in this position, but also if the cat is shifted 1 pixel to the right or 2 pixels to the right. So the question is, these neural networks are working very well, right? They can recognize a lot of things. They can understand a lot of things. They can recognize faces in images. They can recognize animals. They can even recognize and put labels and label complex images, complex scenes. So the question is, are they understanding reality as we know it, right? And the answer is, so far, no. So they are purely statistical methods, and what I'll show you next are cases where these neural networks trained to recognize particular, in that case, animals, pets, failed to recognize. So those are false positives, in this case, of dogs, okay? And you can see that indeed some are dogs, right? But others are not, right? And you can tell, right? You can tell which ones are dogs and which ones are not, but the neural network cannot. Why? Because statistically, a donut is very similar to a dog in almost all respects, in this particular position, right? So those are from the millions of images that were used to train the neural network. A few of them are confused with dogs just because the low-level statistics are not right. And we are not confused by this, at least once we look twice, right? Because we know what a dog is, and we can tell that this is not a dog, right? There are more examples like this, okay? This is other things that are confused with dogs, in this case, fried chicken, right? I think I have a few more, okay? Oh. This is maybe the most interesting, right? You can see that brownies and dogs are actually very similar from a statistical point of view. And what we learn from this is that we actually need to have some higher level understanding to tell us what is a dog and what is a cake, because we understand, even though, as you can see, right, I mean, not that much difference between this. So the answer to this is harder because it's actually there's also this one, okay? So the answer to my question is, will deep convolutional neural networks take us towards AGI? And the first answer is no. Why no? Because even though they are doing a good job at recognizing images, at labeling scenes, at identifying objects in pictures and so on, we know, because of these cases, we know that they are not doing the right thing, right? We know that somehow they are just treating low-level statistics, and they are using these low-level statistics to classify the images. On the other hand, oh, okay, this is one more, but you get the idea. So on the other hand, there is very strong evidence that deep neural networks, deep convolutional neural networks, can do a lot of things very well, Okay? This is actually not done with deep CNNs. This is Watson when it competed in the Jeopardy competition and won against IBM. But those are images, and you probably have seen also now something came out on faces that do not exist that are generated by deep neural networks according to statistics, and that you cannot tell apart from real faces. But those are synthetic videos of people that do not exist and that work as in the TV. This is, of course, a Tesla in self-driving mode. And if you have not yet driven in a Tesla, you'll be quite impressed actually by two things, by how much it accelerates, and then by how well it drives by itself. And probably the most interesting of all, and I will explain why it is the most interesting of all, this program called AlphaGo that learned to play the game of Go, and that learned to play the game of Go.
Can I hear you?
Hi.
Yeah, we have this
I'd like to reserve a table for Wednesday the 7th.
This is actually
For
Google Assistant
7 people?
trying to set up a reservation.
It's for 4 people.
4 people when... Today? Tonight?
Next Wednesday at 6 p.m.
You probably heard this. So
I think it's a man jumping in the air doing a trick on a skateboard.
this is an app
When
that
you're
you can
talking to
download to your
a
phone.
group, sometimes you can talk and talk and there's no response and you think, is everyone listening really well or are they half asleep? And you never know.
I see two faces, 40-year-old man with a beard looking surprised, 20-year-old woman looking happy.
As engineers, we're always standing on the shoulders of giants, building on top of what went before. And in this case, we've taken years of research from Microsoft Research to pull this off.
I think it's a young girl throwing an orange frisbee in the park.
For me, it's about taking that far-off dream and building it one step at a time. I think this is just the beginning.
Okay, this is the video. This is a system from Microsoft, but systems from other companies do similar tasks. This is done with deep neural networks, and as you can see, they do a fairly good job at identifying what is in the visual field, at labeling images, actually at labeling in real-time videos, okay? Now, why did I say that the game of Go was the most impressive demonstration so far of the combination of deep neural networks and reinforcement learning? I have to tell you a little bit of the story. I don't know, how much time do I have to talk here? So 15 minutes more? 10 minutes more? Well, there's no one, so I'll just talk 10 minutes more. So, the first time that a game was addressed was the game of checkers. Checkers, damas in Portuguese, right? The game of checkers in '59. And it's basically a search, right? You have to search in a tree. And this game was programmed by Samuel. And uses something which is minimax and alpha beta search, that if you had the AI, the course you already studied. And so he managed to play very well the game of checkers, okay? But this is purely the evaluation function was crafted by hand, right? Which takes into account how many stones you have and so on. And so there is not machine learning here. Then, a number of years later, actually in 1992, I was at the conference where this was presented. Tesauro presented a system that learned to play the game of gammon, okay? And the way it learned was basically by using reinforcement learning. Remember, reinforcement learning is that learning method where you get the result in the end. If you are playing a game, in the end you won or you lost, right? And that value is retropropagated in time and is used to construct a function, a model of the value function. What is the value function? The value function is the function that tells you the value of each position in the game. If you have a function that tells you the value of each position in the game, let's say +1 is victory, -1 is losing, and somewhere in between is the higher the better. So if you have a function that tells you the value of each position, it's all you need to play a game, right? Because you just need to select from all possible moves, you have to select the position that has the best value, the higher value, right? So what Tesauro did in '92 was actually to show that by using reinforcement learning, you can retropropagate in time the value that you obtain from losing or winning the game, and use that retropropagation to train a neural network that estimates the value function of each board position. This was quite remarkable because basically what you do is you give it the neural network, you give it the rules of the game, and then the system learns to play by itself. Okay? And when Tesaro presented this in the beginnings, some 25 years ago, everybody believed that, well, the next games will come easy, right? Chess, Go, will. It took actually a long time. We eventually managed to create a program that beat the world champion in chess, but the program did not learn by itself. So it basically learned. It's a very powerful computer that does a very extensive search, and the board positions are slightly learned, but still did not learn by itself. So the actual breakthrough came out 3 years ago with AlphaGo. So there are actually 3 versions of AlphaGo. The first version of AlphaGo, which did beat the world champion, okay, was trained on positions played by humans. So basically it was trained on games played by humans, thousands, actually millions of them, I think. And from each game, okay, it learned, I have the scheme here. So, okay, the AlphaGo actually uses 2 networks, the policy network and the value network. The value network gives you a value of each position. So, as I said in the gammon, right? Higher the value, the better the position. And the policy network actually gives you an expected value for each move, right? So if you play here, then it's better. If you play there, it's not so good. If you play there, it's the worst, right? Now, both the policy network and the value network were trained first on games played by humans, and then they were improved by having the system play against itself. Okay? The reason that Go was considered such a difficult game is that the branching of the tree is very rapid because you have hundreds of moves that you can play. So in just 3 or 4 moves ahead, we are in the millions, we are in the billions of possible positions. And in Go, you actually have to look 100 moves ahead. So it's not good enough to look just 4 or 5. So this was a game that was very hard to learn using simple alpha-beta search because you need to go very, very deep, and the number of positions is very, very high. Okay? So the search itself works a little bit like the checkers, the search in checkers, and you look down, you go down the tree, guided by the value of the value network. Okay? Then there is another version of AlphaGo 0, which is much more impressive. So AlphaGo 0, which actually beat AlphaGo by 100 to 0, okay, never looked at the game played by humans. So AlphaGo 0 learned by itself. It played 40 million games against itself, starting from scratch, and became better not only than the world champion, but even better than AlphaGo, which was better than the world champion. Okay? So this was the most impressive demonstration that deep neural networks, deep convolutional neural networks coupled with reinforcement learning could indeed learn very complex things. And then there is AlphaZero. AlphaZero goes one step further because it learns any game. It just doesn't, it not only Go. It learns Go, chess, Japanese chess, and probably any game that you put there. You just set the rules so that it can follow the rules, and then the AlphaZero learns to play any game at a level better than the world champion. In the process, this is taken from the paper that describes, that just came out 2 months ago. And the interesting thing is that in the process of learning chess, right, from scratch, it also learned what are the best openings, something that we did not know until now, right? I mean, this is a concrete, objective description. For instance, you can see this is called the Sicilian, let's say, this is called the Caro-Kann defense. And you see here that white is much better than black in that position. And for instance, this is the Sicilian defense, much more even. So in the process of learning to play these games, this AlphaZero also taught us something that we have played this game for thousands of years, and we still did not know what is the best opening. And this is a very accurate, very objective assessment of the value of each opening. So this is the argument that deep neural networks can indeed not only solve very, very complex problems, but they can actually obtain knowledge that we did not have. But still we are talking about board games, right? We are talking about games where we have all the information in front of us. It's a board. We know the state space. The state space is the number of positions that we can reach from the starting position. The state space is finite, okay, and we can learn. So we say, okay, computers beat us at board games, so what? This not very impressive. So the guys from DeepMind actually took this one step further. And what they did is that they applied the same techniques, the same architecture to play StarCraft, StarCraft 2 in particular. Okay? Now, StarCraft is one of those strategy games. Anyone here that played StarCraft? Okay, a few, so good. So I didn't. I have two, but I still didn't find the time. So StarCraft is a very complex game where you have to do not only the short-term battles with your opponent, but also you have to create the resources and have an economy and create, the troops that you need for battle. And so what the guys at DeepMind did was that they trained a system like this to play StarCraft. I think I have a video.
Let's go ahead and get into that game number 4 out of 5 here and check out how Mana does.
All right. I'm pretty intimidated at this point.
Yes. I am as well. And as
phenomenal unit control. This is not something we see very often.
No.
The stock is coming in from multiple angles as well. A forward blink at this point off a star. Yeah, this is pretty insane stock play then.
That is just unbelievable. Like Mana has made so many immortals this game. I can't even count how high. And the fact that it has been defeated by literally pure Stalker, the unit that the Immortal most counters. It's so surprising. And GG is called by Mana there.
Yeah, so once the BD roll in, I can kind of a bit.
Okay, so now they describe a little bit how they did it, but the interesting thing here is that, can I cut the sound? So the interesting here is that they use the same neural net, a similar neural net architecture that they used to solve Go and chess, and now they applied it in a game that is vastly more complex, that has lots of hidden information, and that where you need to take into account not only what you see on the screen, but also what's it's hidden and outside of you, okay? And the system learned how to play this game. And so this is very convincing evidence that the combination of deep neural networks, reinforcement learning, and some other techniques that I'll tell you in a second, can actually address very, very complex problems. I mean, we are approaching the complexity of the real world. Right? These games are very complex. They have different time scales, short time scales, long time scales. So if you can use these techniques to learn to play this game, you can actually most likely be able to use these techniques to learn other stuff. So why is StarCraft interesting and challenging? Well, first of all, there is no single best strategy, unlike a closed board game. There is imperfect information because there is information that is hidden from the players. You don't know what the other player is doing in the background. It's real time, so you don't have the time to explore the space. The action space is huge, much larger than any board game. You need long-term planning and make it compatible with short-term planning. There is an interface, it's called the Brood War API, that enables you to play in conditions that are essentially the same conditions as a human player. So a system like this that learns how to play the game actually cannot cheat. Right? You cannot fire much faster than a human player or so on because that is imposed by the Brood War API. This is the architecture of AlphaStar. So what they did was they create several agents. The agents compete against each other, okay? The reinforcement learning comes in, so you get the rewards in the end of the game. The reinforcement learning retro-propagates in time the result of the game, okay? And you use this. Then you have a a scoreboard of agents, and you basically sample from this scoreboard using something called the Nest distribution, and you sample from this distribution to basically keep selecting the best players, and the population keeps evolving, right? So supervised learning is where they started by learning with the best players in the world, okay? There's a ranking for StarCraft. Those are the best players there, or at least some of the best players. So it started way down here, and then the population keeps evolving until it's actually better, even better than the best players in the world. So this is very convincing evidence that you can use this combination of techniques to learn almost any game, almost any behavior in a complex scenario.
In recent years, a few outspoken...
So the question and this is the last question I want to ask is, should we be worried? I mean, systems that this has all been done in the last 5 years, right? So should we worry? Can these systems, can this particular set of techniques lead us towards AGI? Can this set of techniques be used to develop systems that are basically as smart, as flexible, as intelligent as we are? If the question is about board games, the answer is yes. If the answer is about strategy games like this, like StarCraft, the answer is most likely yes, certainly for StarCraft, but it's very likely that for any game of this sort, you can do it, okay? For the real world, for real life, we don't know. Okay.
In recent years, a few outspoken intellectuals, such as Elon Musk, Sam Harris, Stephen Hawking, Nick Bostrom, to name a few, have voiced genuine concerns for the rise of artificial intelligence, as brilliant minds across the globe are competing to retrace the hundreds of millions of years of evolution that resulted in the human brain. And while many experts have no doubts about machines' ability to achieve human-level intelligence at some point in the future, just as many believe it to be an impossibility. And perhaps it is. Perhaps we are incomprehensibly complex in such a way that we cannot do what nature has done to us. Then again, if random mutations can lead to intelligence, how hard can it be?
Okay. So this is an open question, right? So we don't know how hard it is to get to AGI, right? Some people believe it's very hard. Some people believe it's impossible, that we'll never be able to understand how real intelligence works. And some people believe we'll be here soon, okay? If you want to read more about this, there are lots of places in the web, of course, where you can learn about this. But I just leave here a few books that I believe are very interesting. So this is Super Intelligence, a book about this idea that if you get to develop human-level intelligence on a machine, nothing stops it from becoming even more intelligent, actually super intelligent, way more intelligent than us, and the consequences of where that could lead us. Ray Kurzweil is one of the apologists of the idea of the singularity, that sometime in the future, probably this century, we will see a very, very fast acceleration of technology, and you'll reach to a point called the singularity. This is a book by two professors at MIT that address the questions raised by this technology displacing human workers in the economy, in the society. This is an interesting and light book about transhumanism, the idea that this biological support of us is just a transitory thing because we can get to something better, which is, to say the least, a radical idea. This is the master algorithm by Pedro Domingos, that was a student and a professor at Technical, but is now in Washington, in University of Washington. A very, maybe somewhat unrealist, but still interesting book that basically argues that super intelligence, AGI, is not only possible, but is unavoidable. So we'll get there very soon, and we have to be prepared very soon to the consequences of AGI. This is also a book on the long-term perspectives of artificial intelligence, starting with the idea that you can have an intelligence explosion fairly soon. An intelligence explosion is this idea where an intelligence system develops the next generation of intelligence system, which develops the next in a spiral of development, and my own book, which covers several of these topics. Okay? I have here a survey. I'm not sure whether it's working. I was not prepared for this. But if you want to try, go there and ask and answer the 3 questions that are there on your cell phone. Let me see. Hope this is working. I didn't try this. Yeah, okay, try it. On your cell phone, there are 3 questions. Please. Okay, raise your hand when you're done. Is it working? Are you done? Okay, need a few more. I see that filling surveys is not your favorite sport. Who is done? Okay, better, a few more, come on, come on. To have some statistical significance. Okay, everybody's done? Sort of. Okay, let's go to the results. Uh-oh. Okay, we'll go for the questions before I do this, okay? I'll look the link up. Okay, any questions? Questions? No?
Testing, yeah. So I think my question is a bit philosophical, probably. But Pedro Domingos wrote a book about the mistake of Descartes. Yes?
The mistake of?
Descartes. O erro de Descartes.
Oh, with Descartes, yeah.
Yeah. So basically, I think.
Descartes' error.
Yeah. I believe that it's that we humans have rationality and we have our emotions. Okay, so they both need to be connected in order to make a conscious being. And this saying, how can we probably manipulate these states, if I can say this, into make a conscious with artificial intelligence?
Yeah, so that is a good question. Let me see, I think I got it now. Ah, that's why. Okay, so that is a good question. The major point of Damasio is that, I mean, the brain does not work on nothing, right? The brain is inside the body. The brain processes sensations from the body. The brain processes emotions from the body, and the emotions are just as important as the rational part, right? And I think he's right. You know, we cannot imagine human intelligence separate from the human body, okay? That is true. But that does not mean that computers cannot have the same sort of thing, right? I mean, there is nothing magic on the brain. The same thing that can take us to artificial intelligence can also take us to artificial emotions, if you want, and to artificial creativity and so on. right? And so there is really nothing that if you have the right algorithms, you can get to that, okay? A more interesting question, and this is a deep discussion between people that work on the RE, is whether you can have true intelligence without a body, right? Whether if you want to have true human-like intelligence, you actually have to have a robot, and the robot has to walk around in the real world and have that sort of contact with the real world to get something close to our intelligence. If you don't have that, and if you are a system working on a computer and just watching YouTube and so on, you'll never get to human-level intelligence. That is probably true. But, I mean, we also not saying that we need exactly human-like intelligence, right? You can have intelligence beings that are not human-like, right? They don't see the world as we do, but they can be intelligent. If we find extraterrestrials, they are not going to be humans. So I think Damasio is right, but I don't think that is an objective on the way to AGI. I think you can get to AGI, both because algorithms can get much of the same stuff that our brains do, and also because you can have AGI on intelligence that are very different from human intelligence, okay? More? Go ahead.
Okay, why do these algorithms still require such a huge amount of data?
Yeah, good question. So that is actually one of the reasons why people argue that deep neural networks will not lead us towards AGI. Because even though when we grow up, we are trained on very large amounts of data, at least that much. I mean, when you grow up in your first 3 years of life, you certainly see much more than 1 million images. So you were also trained on very large amounts of data. But once you are trained, we can learn on small amounts of data, right? If you see a new animal, you don't need to see 1,000 pictures of a new animal to recognize that animal, right? And this is something that people argue that neural networks just by themselves will not take us towards AGI because they do not duplicate this ability we have to learn from small amounts of data. Okay? Still, there are many people working on what is called transfer learning, where you basically learn quickly new things, right? And if we are able to design transfer learning, you can use a network that was trained to recognize cats and dogs and elephants and so on, and then you can recognize, for instance, snakes, just showing 2 or 3 snakes. So right now the argument is true, the technology we have now, but there are people working on transfer learning and on this quick learning that you referred that we don't have. And I don't see that this is impossible. I think it's quite realistic that we'll have that. And we may have systems that just look at 1 or 2 pictures of a car and learn how to recognize a car without forgetting what they already learned. Okay?
Okay, but children, okay, then this would be based on the fact that you need to transfer information. I mean, we are talking about 2 different kinds of problems, and we can apply the same knowledge to 2 different. But children do not do this. We do not work this way. I mean, they can analyze things without this huge amount. They are not transferring information. They're not transferring huge volumes of data from something that they already knew to another thing.
But transfer learning is not that. So transfer learning is the idea that if you have a network that is trained to do some task, let's say object recognition, right? And to do this, it was trained on millions, maybe, images. But once you have the right layers on the network, you can learn just with a couple of images. And this has been shown, and you can do this. And children do this, right? But children to do this, and also animals to do this, before they were exposed to millions of images during the first years. And we know the way the brain develops, that if you are not exposed to thousands of hours, millions of images during your lifetime, you will not learn to see. Experiences with cats have shown, for instance, and some cats were grown up on rooms where they could only see vertical stripes. Their heads were fixed like this, and they could only see vertical stripes, and they did not learn to see any other lines. So we know that you actually need this. So it's not that different, right? It's not that different. It's very likely that we can use these networks to learn quickly as we humans do. I don't think it's outside. It's not in today's technology, but I don't think it's impossible.
Okay, one final question. A lot of people use these algorithms because they have fantastic results. Are they just functions that are optimizing things? Because we cannot explain what they are doing. So
that is true. Of course, the brain is also only a function that is optimizing things, right? I mean, there's nothing special about the brain.
But if the brain, you start with a hypothesis and then you work your way through.
No.
It's like, oh, here.
The only difference about the brain, is that the brain has all, because, I mean, the brain is not magic, right? The brain is just neurons. So the difference, and that is a good point, is that on top of this ability to perceive images and understand stuff, we have some ability to have symbolic reasoning on top of this, right? That's why we can recognize distinguish the donuts from the dogs, because we have this high level. And this we don't have, right? We don't have in deep neural networks. As far as I know, there are no theories to do this, so we don't have any good theory how to put these deep neural networks together with higher perception systems that lead to the symbolic understanding and symbolic explanation that you refer to. So I think in that respect, we are far, and I think that is the most important question. We don't know how to do that, so maybe we will not be able to do it.
Hello. I would like to ask if there is any technique known so far that tries to approach artificially intelligent beings as we are. We are not only brains, we have bodies too. And that makes our whole set of cells that have this DNA, have these different features. Is there any research on this right now?
So that is basically a similar question to what he asked. How important is the body? So there are many people, many researchers that believe that is very relevant. And we have people here in Technical, people at ISR, that have humanoid robots where they try to learn that way, right? They are trying to reproduce the learnings of a child. So they have childlike robots. So there are many research groups that are exactly doing that. They are trying to learn not only by supervised learning like this, but they are trying to learn embodied with the body, right? So the answer to your question is yes, there are many people working in this, and as I said, there are many people that believe that is the only way to go if you want to have something like human level intelligence, okay?
Thank you.
Hello. My question is, what can the society or everyone do to protect themselves against the AI capitalism, so that some tech firms have so much power that the others cannot deal with it?
So you are not worried about smart robots, right? You are just worried about powerful companies. That's your question, right? Yeah? Yes. Okay. Yeah, that's a good question. The point you're making, I was trying to get the survey results. I think you'll have to skip because I don't remember the password. I'll have to check it. So, the password to the survey site. So yours is a good question. The problem with AI techniques is this. As we keep increasing our ability to reproduce human abilities in programs, right? AI, I mean, if you can have systems that can do legal analysis, systems that do medical diagnosis, systems that can drive cars, there will be some tendency to concentrate economic power, right? Because probably just a couple of companies will create all the drivers in the world, right? Right now we have millions of drivers in the world, but maybe 50 years from now, there will only be 2 or 3 or 4 companies that make all the drivers in the world because the cars will drive themselves, right? In the same way, maybe there will be companies that make 90% of all medical diagnoses. So there is this sort of technology, as all technology, but this sort of technology has the power to concentrate economic power, right? I think that's, who asked the question? You. So I think that's a real thing. So what can we do? Well, one answer is we prohibit the development of AI technology. So that is a good answer, because we don't want this. This is too dangerous. First, it's too dangerous, and second is it will concentrate economic power too much, which you don't want. I don't believe this is possible, because it will be very hard to stop people from developing AI technology. So I think we will have to find the mechanisms to force some redistribution of income, right? I don't know what these methods are. People have argued about guaranteed universal basic income, where every citizen, every person on earth gets some money, even if he or she doesn't work. That's one way. Other people have proposed tax the robots. So if a company is using robots or assistants or smart systems, then you can tax them if you were to tax persons, and use that to redistribute the riches. Or maybe you can pay the people who provide the data, which is critical to develop these systems, right? Right now, you are giving away your data to Facebook, to Instagram, to LinkedIn for free, right? Most of you don't get paid to be on the social networks, or even to go to Google, make searches, which Google uses to push you ads, right? So people argue that we should be paid to get this data, and then if you get paid for this, it gives some redistribution. So anyway, my answer is, it's a difficult question. I don't know the answer. I think we'll have to find some redistribution mechanism which does not exist today. And I think we are seeing a tendency of concentration of economic power. If you read the latest book by Pinker, he argues that it's true that asymmetry in income is increasing, but it's still true that even the poor are getting richer. So you may say, as long as everybody is getting richer, it doesn't matter if some people get very, very rich, right? It's an argument. It's interesting to read this book, and chapter 6 of his book, where he argues that, yes, asymmetry in income is increasing, but we are all getting richer. So it depends a little bit. But of course, people don't like if they have people much richer on the side, right? So it's a problem that we have to address. I don't think we are doing enough to address it today.
Hello. My question is kind of strange. All around society, we have certification. If you want to be able to drive, you need the driver's license. If you want to be able to go to university, you have to get a course. Since machines are learning by themselves, how will you certify a machine? How do I know that the machine doesn't just kill black people and not white people? How do I know that it's learning the right way? There is no certification. They're learning alone. It's their own rules.
Yeah, one of the, your question is one of a very important question that is asked is, we don't know what these networks are learning, right? These networks have hundreds of thousands or millions of weights, and you cannot know, or at least it's very difficult to know what they are learning, which means they are sort of black boxes, right? If you have a black box driving a car, you don't exactly know whether the car is going to behave well in all conditions. To be fair, you also don't know if a human will behave well in all conditions, right? And so this is engineering. There is no zero error, right? So what we want to make sure is that the car will not create more accidents than a comparable human driver, right? Which is a good point. And also, if you want, that will also not have specific biases, right? Like killing children or women or whatever, right? But the point is, this is engineering. We'll never get to zero error, but we can have the same sort of certification, right? The cars will only be loose on the street once you have enough confidence that you'll have less accidents than human drivers. And this is actually already true. The cars like a Tesla or so on has less accidents per mile on autonomous driving mode than with the human driving. Not so much because it's a better driver than the human, but because it does not get as easily distracted as humans do, right? By phones, radio, girls passing on the side of the street, that sort of stuff. So it's very likely that these systems will decrease the level of accidents compared with human drivers, just because human drivers get easily distracted.
So I have two different questions. The first is, how important are the pre-tendencies of the algorithm? Like, if it should be curious and look for new data to be more intelligent.
How important are the?
Predispositions like being curious or try to do things fast, or instincts to explore.
The algorithms that they exist now, they don't have those. They don't have those abilities, right? The algorithms that I used to train neural networks, they are just a mathematical algorithm that minimizes the squared error, right? That does not exist. Now we can think about meta heuristics on top of the algorithms. For instance, when you are doing reinforcement learning, there is a trade-off. So you can always do the best possible move, or the move that you believe is the best, or you can do which is called exploitation, where you exploit what you know, or you can do, I think this move is better, but there is this one that also is not so bad, and I would like to learn more about it. So this is called exploration. This is called the exploitation dilemma, right? Which you can be viewed as curiosity. If you do more exploration, you are more curious in exploring new things. And if you are doing exploitation, you are just doing over and over the things you did better. So those are important trade-offs. We know this about robotics. This exploitation-exploration trade-off is a very important parameter in setting when you are trying to find the best player, for instance, because if you just do exploitation, you'll never learn, right? Because whatever you know in the beginning, you'll always play the same way. So you have to do some exploration. On the other hand, if you do a lot of exploration, you are not choosing the best move, so you are not playing as well as you could. So this idea that curiosity, exploration, but those are things that are encoded in the algorithms, and once you tune them, they just run, right? So it's important on the performance of the algorithm, but those are things we know how to tune. They are called hyperparameters that we know how to set.
And the second question is, can we find out something new about intelligence? Like, there's no such thing as a general intelligence, just many specialists, and some specialists are really good at some area, and you need another algorithm or another personality of the intelligence to be better at another area, like some for humanities and another for science.
Yeah. So if 70 years of research in AI have told us something, is that there are indeed many types of intelligence, right? Things that people believed will be hard to do, like demonstrating mathematical theorems that you just heard about in the talk before, or playing chess at world level, or optimizing schedules, are actually things that we manage to do very easily. So things that we believe, or making complex computations, symbolic integration, for instance. Actually, we know how to do that. It's almost as easy that we don't even call it artificial intelligence. On the other hand, other things that were believed to be easy, like looking here and recognizing the faces of the audience, turned out to be very difficult, and we can only now start to do them, okay? So what we learned is there are indeed many types of intelligence, and if you want something like general AGI, we'll need to combine them all, right? And we need to understand them all. And we may do a few better and others not so well. The problem is that we really don't know very well how to combine them. It's hard to combine this ability to walk around and recognize obstacles with long-term planning and so on. And if, I guess this is the last, right? We are closing. And if these things that I told you about StarCraft reveals something, is that reinforcement learning coupled with deep neural networks can actually do a very good job at matching long-term goals and short-term goals. Because this system learned not only to play the battles, second-by-second battles, but also to develop the economy that is behind to have the armies and so on. And so this is rather impressive evidence that these methods can have a lot of mileage and can take us very far. Okay, I think this is it, right? Okay, thank you.
That was the last question. We'll now give away the last prize. Thank you very much to Professor Arlindo, and I hope you enjoyed this edition of SINFO.